Swayam Prabha. Digital India. Educated India.
Welcome to the 13th lecture in our NPTEL course on particle characterization. So far in this course we have covered particle characterization in one very important aspect, that is morphological characterization. So we have discussed shape and size characterization in the previous lectures. Today we are going to move on to talk about structural characterization of particles and also the interfacial characterization of particles. The reason that we need to take these two together in a sense is because when you look at a particle as a whole, you can actually divide its volume or its structure into three different regions. So, if this is a particle that is suspended in a fluid, and let us say this could be a solid particle or it could be a liquid droplet, the part of the surface or part of the particle that is visible to us is the exterior boundary, and that is the interface between essentially two bulk forms of matter. You have the solid or liquid particle that is sitting there and it is suspended in a fluid, either a gas or a liquid, and these two represent essentially two bulk systems that are adjacent to each other, and the surface of a particle represents the interface or the line of discontinuity between these two continuous faces. So, the outermost profile of the particle is what we call the surface, the region just beneath the surface. So, this area that is adjacent to the surface, but just below the exterior surface is known as the subsurface region, and as you keep moving towards the center of the particle, you will eventually reach its core or interior of the particle. So, in terms of the structure of the particle, these are very distinct regions, and we really need to appreciate the similarities and the differences between them. Now, go back to the surface. As I said, it represents essentially the contact point between the discrete particle that represents one face and the fluid which it is suspended in, which represents the other face. Now, clearly there is a huge difference in properties of this particle phase and the surrounding fluid phase. Density is different, everything is different, energy is different, surface tension is different, hardness is different, composition is different. So, there is a huge step difference that happens at the interface between the particle and the fluid that it is suspended in. However, that assumes that the surface itself is a two-dimensional area. Now, when you say surface, what you think of is basically two dimensions, right? But if you look at the external surface of a particle more closely, what you will find is that it is really not a two-dimensional area, but actually a three-dimensional volume. And the reason for that is the exterior surface of a particle typically tends to be quite rough, unless it has gone through some special processing to improve its surface finish by orders of magnitude. You are going to see surface roughness asperities that are of the order of microns or at least nanometers. So, the surface itself, it is not a clean line or plane of discontinuity between the fluid phase and the solid or liquid phase. Instead, you see a roughness profile on the surface of the particle. So, what that means is this interface is now actually a volume, because it has 3 dimensions to it. So, for example, if you have let us say a liquid that is in contact with the particle, the way that it actually encounters and interfaces with the particle is going to be different depending on the actual location on the surface where the contact or the interaction happens. So, for example, if the liquid contacts this point, it is actually going to try and fill up this asperity, right, whereas if it contacts it on a smoother area, it is going to spread itself differently. So, even surface wetting by the fluid will be very different in its nature depending on whether it is a smooth profile or a rough profile. So, the key point, one of the first key points to remember is that even though we say particle surface and imply that it is a 2-dimensional surface, in reality the particle presents a 3-dimensional interface to the fluid that is surrounding that particular particle. And similarly, when you have 2 particles that are close to each other, which are adhering to each other, the interaction between 2 solid particles will again reflect the 3-dimensionality of the particles. So, depending on the relative roughness of the 2 particles, you may see more or less interlocking. For example, if the roughness asperities align with each other, you can actually get an increased surface adhesion force. On the other hand, if you have a smooth particle coming in contact with a particle that is relatively rougher, the contact area can actually be significantly reduced, and therefore the interparticle adhesion forces will also be reduced. So, I mean, think of it this way: if you have one particle that has a profile like this and relatively the other particle has a profile like this, then the contact areas are very isolated, right? They are making contact only at these locations. So, since adhesion forces essentially depend on the area of contact between the surfaces, this will represent a case of very low adhesion force. On the other hand, if you have 2 rough surfaces and they happen to align themselves so that the roughness kind of fits in, which they will, I mean, surfaces have a natural tendency to accommodate each other, the adhesion force in this case may actually be significantly higher compared to the adhesion force on this side. So, that is why it is important to appreciate the 3-dimensionality of the surface that you are considering. Now, if I look at the properties of the surface, they are going to be actually a mix of the property of the solid or liquid particle and of the contacting fluid, because it is a volume fraction phenomenon. Because it is a volumetric interface, if I just take a slice of this surface and estimate the volume percentage of the fluid on the surface, which would be essentially the volume that is occupied by fluid to the total interfacial volume. So, this is your fluid volume percentage. This parameter actually has a huge influence on the properties of the surface itself. The higher this volume percentage, the more the properties of the surface are going to reflect the properties of the fluid. I mean, in the extreme case, if the entire surface is inundated with the fluid, then the particle surface will essentially behave just like the fluid, right? Or in the other extreme case, if the particle is such that it repels the fluid that it's suspended in, so that the fluid is not able to wet the particle, the particle is not able to absorb the fluid or absorb the fluid, then this volume percentage is going to approach 0. In that case, the properties of the particle surface are going to be essentially the same as the particle material itself. So, the interfacial characteristics are very important in determining what properties the particle surface is going to have relative to the fluid that it is in contact with. But it will be a very sharp gradient, because you are essentially transitioning from a fluid to a solid or liquid phase. This subsurface region, on the other hand, provides a much more complex picture, because here what you will see is the more gradual gradient of properties compared to the surface of the particle. So, if this represents the surface, so this is your solid or liquid particle, and then this is your fluid, and let us represent this as a line of discontinuity between the particle and its surroundings. What we call the subsurface is basically the region that is just below the surface and extending some distance into the particle phase itself. Now, what are you going to see between here and here? You will see gradients in properties. So, what are the properties in which you will see gradients? Physical properties, chemical properties such as composition, stresses, defects, etc. I mean, virtually any parametric that you use to characterize a surface will show a gradient as you penetrate further into the particle, and that immaterial how fine the particle is. You will see this type of gradient behavior even for a nanoparticle. Certainly, as the particle size increases, the gradients themselves will be extended over a longer distance. However, the magnitude of the gradient may still be just as large in a nanoparticle compared to a micron sized or a millimeter sized particle. In terms of chemical properties, what do we mean by that? For example, composition. Why would the composition of the surface be different from the composition of the subsurface? Well, one obvious reason is the surface is exposed to the fluid. So, for example, if it is in an oxidizing atmosphere, the surface may have an enrichment of oxide, whereas depending on how many diffusion paths are provided, the oxidizer may never be able to diffuse into the bulk of the particle and cause subsurface oxidation. So, the subsurface may still be, for example, metal, the surface may be a metal oxide. That is a simple example. Oxidation is a process that happens naturally, right? But you can also think about manufacturing process where we are deliberately introducing a reactive gas to achieve a certain purpose. For example, when you have steels that have low carbon content and you want to increase the carbon content, there is a process called carburization that is used, which essentially takes carbon molecules and lets them diffuse into the steel surface in order to enrich the carbon in the steel alloy. Now, that is an example of, again, a chemical or compositional gradient which will then exist from the surface to the subsurface. And the reason for that is that the the process by which you are introducing the carbon into the metal, into the alloy, is through a diffusion process. So, typically you would take a carbon containing species and let it diffuse into the metal. For example, it could be something as simple as carbon dioxide, or it could be some organic carbon like methane and so on. So, what would happen is this species will diffuse with some diffusivity. So, let us say that you are using methane to achieve this carburization. This CH4 will essentially first encounter the surface of the alloy and it will leave behind carbon and therefore increase the carbon content. But then by controlling the amount of diffusion of this carbon containing species into the matrix of the material, you can control the depth to which this carburization happens, because the distance that this species will travel within a certain time can actually be calculated, and in fact the diffusion distance S is roughly given by a constant multiplied by square root of d times t, where d is the diffusivity of the species and t is the time over which the diffusion is occurring. So simply by controlling this parameter, the time parameter, you can control the depth to which diffusion happens, and thereby you can control the depth to which, for example in this case, carburization happens. Another example would be nitridation. Again, you want to add nitrogen to an alloy material. This is typically done by pumping nitrogen gas over the alloy under pressurized conditions in order to improve diffusion rates and diffusion coefficients, and you will again see this type of behavior. It is basically a square root dependence. You take the diffusivity of the species, multiply it by the time, and take the square root. That basically gives you the time dependence of the depth of penetration by this reactive gas. So essentially you can not only introduce a chemical gradient, you can actually control it when you are doing it essentially as part of a manufacturing process. So an example of this would be, let us say you have aluminum metal and you expose it to an oxidizing atmosphere, you are going to form brown layer, right. The aluminum will turn brown. It is basically aluminum oxide which has formed on the surface. However, the aluminum core itself still remains as aluminum with just a surface layer of aluminum oxide. But if you now let the penetration continue, let us say that you have a very porous aluminum particle and this oxygen can diffuse into the interior of the particle, then the composition of the entire particle will slowly change, and the particle itself will eventually be converted from an aluminum particle to an aluminum oxide particle through the surface and the subsurface regions. Now will the core of the particle also be converted? That is very unlikely to happen. When you are using, in other words, you cannot convert metal, aluminum metal to ceramic alumina simply by exposing it to oxygen. That is basically what it means. However, you can change its external surface to aluminum oxide, and you can change as much of the subsurface as you want to aluminum oxide by providing a diffusion path and by controlling the concentration of the diffusing material, the pressure that you are applying, the temperature at which you are applying, and most importantly the time for which you are exposing that material to the diffusing species. Now if you look at the subsurface in more detail under a microscope, you will see some interesting things. So again, if this is your surface and then this is your subsurface layer, one thing you will always see is voids or porosities in the surface which allow material to seep into the subsurface. It is very rare that you find a surface that is so integral, that is so perfect that nothing can diffuse beneath. I mean, diffusion can happen even through molecular dimensions. So as long as you have a 10 angstrom opening, vapors will get through. So it is virtually impossible to entirely prevent diffusion of vapors through the surface into the subsurface region. The way that in particular liquids get through is slightly different. Vapors, as I said, can penetrate no matter what you do, unless you have a single crystal which has absolutely no openings of any kind. But most materials are not like that. They are either metals or alloys or composite materials where there is sufficient openings basically in the way the material is put together to allow for diffusion of species. But liquids will not be able to penetrate into a solid surface or another liquid surface that easily. In particular, when you have a liquid that's interacting with the solid surface, in order for the liquid to wet beneath the surface, you need some capillary action. So there are two types of capillaries that exist. One is the blind capillary, and the other type is the open or interconnected capillary. So here the material or the particle wicks the liquid in through a capillary action that is driven by surface tension and viscosity based processes. The capillary itself can end at a dead end somewhere, and that is called a blind capillary. So depending on the length of the capillary, that tells you how far into the particle the liquid can penetrate, or the particle could be could consist of several interconnected capillaries. Now when this happens, the propagation of the liquid through the particle will be much more extensive, and it can get transported not only at its local area of entry, but throughout the surface, and there is a possibility that this can actually extend all the way to the core of the particle. So depending on what you are trying to achieve, you can either try and minimize these capillaries or try and maximize the capillaries, depending on how extensive an interaction you are looking for between the surrounding fluid and the particle that is suspended in this fluid. Now the other kind of thing that you will see in the subsurface are the grain boundaries and the phase boundaries. So if you have a multi-grain structure, you may see a line of separation between the grains. So as you increase your magnification or you start using an atomic force microscope, you can actually start seeing where these grains are laid down. So essentially you can start seeing the way that the material has been packed into its form, right? And again, the boundaries can be between different grains, for example in a crystalline material. It can be between different phases in a, for example in an alloy or a mixture compound, and they represent again lines of discontinuity between one distinct entity and another distinct entity in the matrix of the particle. The other thing that you will normally see is what are known as fissures. A fissure is essentially where the surface has broken off. So it's like a chip in the surface. Now it's a type of surface defect unless the fissure is caused intentionally, but for the most part a fissure is not something that you put in as a design. It's something that happens because of damage over time. The fissure again can be of various types, but usually they are closed structures, and usually they don't penetrate very far into the material. So they are confined to probably a few nanometers, at the most a few microns of the surface region. And the other feature that you would see is if there is a coating on top of the material. Let's say that this is your surface and then you put down a coating on top of it. This coating or plating can actually penetrate into the subsurface also. It's very difficult to do any kind of surface treatment, whether it's painting or coating or plating or passivation, anodization. All of these are supposed to be surface processes, but in reality again it's almost impossible to control them in such a way that they only act on the surface. There is some penetration always to the subsurface region. So a coating is supposed to just go on top of the surface, but what we typically find is that there is a fragment of it that is beneath the surface in the subsurface region. So if you do a metallographic analysis of the material, of the particle, you do a cross section and actually look at the particle and its structure by depth as you go from the outer surface to the center or the nucleus of the particle, you will see all these things. On the surface you will see essentially the surface characteristics. and if you have a very sensitive way of detecting, you will see the 3-dimensional morphology of the surface. But the amount of detail that you see will increase when you go to the subsurface region because of the presence of all these different things that can happen, and at the same time you are seeing all these gradients, right. So if you are using a SEM EDX type of analyzer, you can actually see a gradient in the composition of the material. If you are doing a measurement of for example, if you are using an XRD for your characterization, you will see a gradient in the crystalline structure of the material. The other thing that you will find is that just like in this case where the volume percentage plays a huge role in determining the properties of the surface, similarly the properties of the subsurface are also affected by the volume percentage of the fluid that has penetrated into the subsurface region. So this volume percentage remains a key metric. The difference is, in the case of the surface, the volume of fluid penetration is basically dictated by its ability to fill the 3-dimensional structure which represents a surface, whereas the volume percentage of fluid in the subsurface region depends on the nature of the subsurface. For example, how many capillaries exist, essentially how many paths exist by which fluids can enter using surface tension as the primary mechanism. How many fissures exist, obviously if there is more broken chips or fragments of the surface which allow a physical opening, it's easier for the material to penetrate through to the subsurface. So the volume percentage is still the critical parameter in deciding how the properties of the subsurface vary from the properties of the surface and how that varies from the properties of the fluid that is surrounding. Another important consideration is when you take a surface and you put down something on top of it like a plating or a coating, the surface itself now becomes part of the subsurface. So that is something that is important to appreciate, that our definition of the surface must be consistent regardless of its composition. So if you have, for example, a steel table that has nickel plating on it, then the surface is not steel, it's nickel because that is the surface that is exposed to the surrounding fluid. So we have to be very clear in our definition that what we what we call the surface is not based upon the material that it's made of, but rather the physical surface that comes in contact with the environment. So as you build up a coating on top of it, this becomes part of the subsurface, and the properties will now start showing a variation right from this point onwards. So the gradient, the reference point for the gradient also shifts to the exterior surface of the coating or plating or whatever you are doing. So the surface and subsurface are actually very similar in character, except that there is a gradient of properties between them. However, the third component of the particle, which is the core or the nucleus or the interior of the particle, is distinctly different in its properties compared to either the surface or the subsurface. The core is actually the purest representation of the material itself, because the external processes can change the properties of the surface and the subsurface, but except under exceptional circumstances they are not going to be able to change the core of the material, which will remain intact even through extremely intensive processing. So that applies once again to physical properties, chemical properties, stresses and defects and so on. The core will retain the properties of the original material that this particle is made out of. Now in particular, we try to characterize the core by its defects, because again it represents the purest form of the material. We are interested in the defect level that is present in this material, because that has a huge influence on, for example, the functional properties of the particle itself. So we are interested in defects which can be of various types. So if you look at the core of a particle and you look at defect types, there are really three of them: line defects, point defects, and area defects or planar defects. So a point defect is basically, as the name suggests, a defect that occurs locally at a single isolated location on the material or the core. A line defect is one that is essentially has a linear dimension to it, and an area defect or planar defect or surface defect is one that has an area associated with it. So it's basically a two-dimensional defect in the core of the material. Now most materials will exhibit one or more of these defects. It's again virtually impossible to find a defect-free material. Now what type of defects are we talking about? The defect could be anything from an external impurity. For example, even if you are talking about a pure metal that has just been excavated from a mine, the process of the excavation may have transferred some material or an impurity to this particle, which has become embedded in the core of the material. So that type of defect is basically an impurity defect, or it could be a defect that's more fundamental to the material itself. For example, the material may be supposed to have a certain crystal structure, but during its formation the crystal structure itself might have been altered. There might have been some slips, some stress formations that led to a collapsing of the crystalline structure. So the defect may be essentially an imperfection in the crystal character of the material. So there can be different types of these defects that are visible only when you actually penetrate all the way down to the core or nucleus of the particle. You will not be able to get this type of information simply by looking at the surface or the subsurface, because they are being influenced by too many parameters that play a role in determining their properties. Another type of defect that is frequently found in the core is just pores. Now porosity is a huge problem in the manufacturing industry, particularly when you are doing castings. You are trying to cast the material in its purest form. If during the casting process you actually trap a gas, for example, inside the material, it eventually shows up as a porosity in the material. Now porosity has some strong implications for the usability of the material in the process afterwards, because the more porous the material is, the weaker it is. So it actually has an effect on the mechanical strength of the material. But a more porous material is also more susceptible to its exterior environment, because virtually anything can penetrate through these pores. So the characterization and control of porosities is very important, and here we have basically two kinds: the discrete pores and continuous pores. Again, the difference is in the degree of the problem. If you have discrete pores, the situation is to some extent under control, because the effect of the pore is localized to the area where it's found. However, when you have continuous pores, it's just like the interconnected capillaries that we saw earlier. It essentially provides a path throughout the entire particle for any of the harmful effects associated with the porosity to propagate. So as far as possible, you try to obtain a material that has zero porosity, which is very difficult to achieve, or your fallback option is to discretize the porosity so that they are not continuous in nature. Now a lot of attention has actually been paid to manufacturing processes, particularly casting processes, to obtain pore free structures. For example, vacuum casting is one where by applying vacuum you evacuate all gases from the immediate vicinity of the material as you are casting it, so that the chances of actually leaving the gas behind as an impurity during the casting process is greatly reduced. So, much progress has been made in reducing these pores. Now, another type of defect is voids. Now, a void happens kind of for the reverse reason that a porosity happens. Porosity happens because you have some trapped gas which is not completely vented when you do the casting process, so it prevents complete closure of the material. A void, on the other hand, is something that happens when a material that is supposed to be present in the particle or the surface that you are casting is unintentionally removed during the process, thereby leaving a cavity or a gap, and that is basically what we mean by a void. So, the presence of voids, once again, is most sensitively detected when you section all the way down to the core of the material. It is not immediately obvious when you are looking at either the surface or the subsurface of a particle. Okay, so essentially we have discussed the three regions somewhat in sequence. First, we talked about the surface, what are some typical characteristics of the surface and what affects these characteristics. Then we talked about the subsurface, and then we talked about the core of the particle. Now, in terms of particle characterization, which of these should you be concerned about? For example, if you are a process engineer and you are using the particle, let us say as a catalyst, right, to run a chemical reaction. Now, the aspect of the particle or the critical feature of the structure that you care about the most would be the surface and the subsurface regions. Now, the subsurface region is important in that case because the reactants need to diffuse into the subsurface, and that depends on the nature of the subsurface region, but more importantly the products that are formed have to diffuse back out. So, there has to be a sufficient pathway provided to ensure that both diffusion of reactants in and diffusion of products out happens. So, as someone working in the catalysis industry, where you do not really care so much about the purity of the core material, what you really care about is surface area available to me per unit volume of the product, right. And what I want to try and do is increase that surface area as much as possible. So, I want a porous structure, I want the reactants and the products to be able to diffuse easily down to the subsurface region and then back out. So, I am not interested in hermetically sealing the surface so that everything only happens on the surface. What I really care about again is the total catalytic area which promotes chemical reactions between the various reactants and to produce product. Now, let us take another application such as use of particles in, say, in the pharma industry, where you are taking some kind of a powder, let us say, and you are compacting it to form a tablet, right, which is then packed in a bottle and sent to the patient for consumption. Now, here what do you really care about from a structural viewpoint? How important in this case is the core or the nucleus of the particle? Well, obviously it is very important because it is a medical application. The active ingredients are typically packed into the interior of the particle or the core of the particle, right, and then the material is provided various coatings in order to keep it intact during shipment and storage and so on. So, in the case of pharma, the importance is almost in reverse. The most important part of the tablet is its core that contains the medicinal ingredients, and then the subsurface. Is the surface important in a tablet? You can take a tablet even when it looks like it's in bad shape, right. You have been leaving it in a bottle in a humid environment for a long period of time. The outside of this tablet or capsule might actually look very bad because of all the degradation due to the exterior environment, but if you take it, it will still work, right, as long as the expiration date is not been passed. So, clearly the exterior of a tablet is more cosmetic in its effect and not functional. The functionality of a pharma particle comes primarily from its core. So, if I am trying to do structural characterization, I would put a lot more emphasis on making sure that the core ingredients are consistent from lot to lot and not care so much about what happens to it if it is exposed to high temperature and high environment and high humidity and so on. Yes, the customer would like to see a tablet be intact and in good shape for a long period of time, but as long as it works, they are going to be happy, right. Another application that we can think of is things like let us take detergent powder, right. Now, in the case of detergent powders which are typically formulated in a spray dryer from a detergent liquid, if I am trying to characterize the detergent powder, what structural parameters should I be concerned about the most? Detergency comes from the ability of that chemical to essentially wet the surface of the object being washed and essentially provide a mechanism to lift the particles off the surface. We will talk about this in more detail later on. So, what is the most important characteristic of a detergent powder? It should be able to dissolve well, because if it is coming as a dry powder and you put it into water, it should be able to dissolve well and immediately, and the active ingredients, the surfactants that are in the formulation must be able to quickly penetrate into the surface between the dirt particles and the surface that they are sitting on in order to provide maximum detergency. So, in this particular case, how important are the surface characteristics? They are pretty important because in order for it to work, you have to have almost a complete and instantaneous release of the active ingredient once the detergent is mixed in, for example, with clothes or dishes that it is supposed to wash. But it should be very stable until that point. So, the way that the detergent package is put together, the size distribution for example is very important, but structurally what we would like to see is a uniformity of its physical structure and its compositional structure throughout its cross section. We do not want to see a huge gradient in the properties of a detergent powder going from its surface to subsurface to its core. We want the detergent particle, every detergent particle to be identical to every other, so that every time the customer takes a scoop of the detergent powder and puts it in, they get virtually the same washing result, right. So, consistency and effectiveness are the most important things. So, from a structural analysis, the way I would probably do the inspection is to look at the particle under some kind of an optical microscope to ensure that surface characteristics remain the same. For example, you want to see if the spray dryer is normally producing spherically shaped powder material, you do not want to see that change over time. So, the physical structure of the material should remain constant. And in terms of any compositional analysis I would do certainly some type of FTIR analysis to make sure that the active surfactant is present in all of these detergent particles to the same extent, that it is uniformly distributed. So, different considerations depending on different applications that we use these particles in. Another example would be in microelectronics we use abrasive particles to do polishing of surfaces. In this case, the most important structural aspect is the crystallinity of the material, because what you need to do in order to have good polishing is to have a highly abrasive surface in contact with another surface. So, abrasiveness and hardness are very important parameters or physical properties of these abrasive particles that are being used, and you achieve that primarily by controlling the structure of the particle. As long as you can maintain its crystallinity, it is likely to be able to perform its function. But for example, let us say you are using silicon carbide as the abrasive material, you expect a certain structure of the silicon carbide, you expect to see a certain crystallinity, you expect to see a certain shape, it is all in the exterior of the particle, because abrasion again is a surface process, the core of the particle never gets involved, right. So what you want to control, what you want to characterize in that case is the surface region and possibly to some extent the subsurface region. You would not even care to go into the interior of the particle and analyze it, as long as your purpose is only to be able to control the polishing process effectively. So just like with shape analysis and size analysis, structure is something that you can define and measure to whatever extent you like. You can make it as detailed an analysis or as simple an analysis as you want. The key thing is to relate it to what you are trying to achieve. Now there are certain techniques that are used for structure characterization, such as XRD, AFM, which are very powerful techniques, and we will discuss these in more detail in one of the later lectures. But the question you have to ask yourself is, do I need it? Is that really going to give me useful information, or am I better off simply doing, say, an optical inspection of the particle to verify that the outer surface is in control, or maybe I should do something like a porosity test to make sure that the porosity of the material has not changed, its compactability, which is more a function of the particularly the subsurface. Flowability is another parameter that you may be interested in. In that case, again, what you most care about is the outer surface and the subsurface regions. So mentally you should go through a list of what are the important functional features of the particles in your process and customize your structure characterization techniques to these functional properties that you are trying to achieve. Do not overdo it and do not underdo it, okay. Alright, now in terms of the interaction of the particle with its environment, obviously the surface is where it all starts, and so when we talk about interfacial characterization or the determining the ability of the particle to interact and react with its environment, our analysis is typically confined once again to the surface and the subsurface region. So in the next lecture we will start by discussing how the surface characteristics of a particle dictates the nature of its interaction with the surrounding system. Okay, let us stop at this point. Any questions? Okay, see you at the next lecture then.